Okay, we're going to finish this up with the fundamental theorem of algebra. Basically, this says if a function is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. Now, what you have to remember here when we say complex is we're not saying non-real, because all real numbers are also complex numbers. So basically, we're just saying that every polynomial of degree 1 or greater has to have at least one root. So it might be real or it might be complex or whatever. Okay, so then that leads us to the linear factorization theorem. If f of x is this polynomial in this form where n is greater than or equal to 1, and of course this just means that the lead term is not 0, the lead coefficient is not 0, then basically what we can do is we could actually factor this into the lead coefficient times a bunch of binomial factors, where you would say x minus c1 times x minus c2 times x minus cn and so forth, where you have c1, c2, and all the way out to cn are complex numbers, possibly real, and they may not be distinct. So basically, a degree of polynomial n can be expressed as a product of non-zero constants and n linear factors, where each linear factor has a leading coefficient of 1. So let's start out with, let's look at this example. If you remember this example, we actually had roots, 2 occurred twice. So that would give us these factors, x minus 2 times x minus 2. Or if you want to say x minus 2 squared, quantity squared, but it's x minus 2 times x minus 2. And then we had these two non-real roots. So if you subtract the first one, you're going to get x minus that, with x minus this. X minus negative 2 plus 2i would be the same as x plus 2 minus I. And then x minus negative 2 minus 2i would be x minus 2 minus 2i. So actually I left off the square root of 2 here, but it should be 2i square root of 2 here and 2i square root of 2 here. So that's my bad there. So let me pause the video and fix that real quick. Okay, I corrected that and I made it where it actually made a little more sense. So since 2 is a root, you're going to have a factor of x minus 2, and since 2 is a root twice, you'll have another factor of x minus 2. Now, you're going to have another root, x minus the complex number minus 2 plus 2i square root of 2, and you're going to have another root, x minus the complex number minus 2 minus 2i square root of 2. Now, before I had this as plus, but that's because you could say this is plus 2 minus 2i square root of 2, and you could say this is plus 2 plus 2i square root of 2. But I wanted to go ahead and rewrite it so that it's written in this form exactly, where it's x minus the roots. So that way it makes a little more sense for you. So basically that's what it says. It can be written, any polynomial can be written that way. Now, this next question says find a 4th degree polynomial f of x that has real coefficients minus 2, 2, and I as zeros. So, and it's got to have a real coefficient, but the zeros are minus 2, 2, and I. And also we know that f of 3 equals negative 150. That's going to help us find the actual correct coefficient. Now, since I is a factor then since I is a factor, then minus I must be a factor. Because remember, if a plus bi is a factor, then a minus bi is a factor. Well, I is like 0 plus 1i, so 0 minus 1i must also be a factor. So we know that these four are the factors. X minus negative 2 would be x plus 2, and then x minus 2 would be x minus 2, and then x minus I would be x minus I, and x minus negative I would be x plus I. Okay, so by the factorization theorem, we can actually write this function like this, where we have some constant here, a sub n times x plus 2 times x minus I times x minus I times x plus I. Well, we can figure out that constant by knowing that f of 3 is negative 150, because basically I can just plug 3 in here everywhere there's an x. So if I plug 3 in the first factor, I get 3 plus 2, and then the second factor I get 3 minus 2, and the third factor would give me 3 minus I, and the fourth factor would give me 3 plus I. Well, if I figure all this out, 3 plus 2 is 5, 3 minus 2 is 1. Now if you multiply 3 minus I times 3 plus I, you can do this on scratch paper if you want to. That's going to be 9 minus I squared, which is actually going to be the same as 9 plus 1. So you're going to have 5 times 1 times 10. So this is going to equal 50. So I'm going to have a sub n times 50 equals 150. So then I can easily just divide both sides by 50 and get that a sub n equals 3. And so that coefficient has to be 3. So it's going to be 3 times all of this. Okay? Okay, now we're going to talk about Descartes' rule of signs. And you know what they say, never put Descartes before the horse. Yeah, that's a lame math joke. Okay, so anyway, let's say f of x is equal to this polynomial, and it has real coefficients. Then the number of positive real zeros of f is either the same as the number of sign changes of f of x, so this can get a little confusing, or less than the number of sign changes of f of x by a positive even number. Okay, so if f of x has only one variation of sign, then f has only one positive real zero. And then the number of negative real zeros of f is either the same as the number of sign changes of f of negative x. So here you go. Now you're going to have to figure out what f of negative x is for this particular theorem. So, or it's less than the number of sign changes of f of negative x by a positive even number. And if f of negative x has only one variation of sign, then f of x has only one real zero. Well, let's put this in action with an example. If you look at this problem, you can see it goes plus, minus, minus. And by the way, they have to be in descending order. Plus, minus, minus, plus, plus, minus. So I see a sign change from here to here, a sign change from here to here, and a sign change from here to here. So that's 3 sign changes. So based on that, let's see, what have we got here? It says the number of positive real zeros of f is either the same as the number of signs, so it has to be either 3 or less than the number of sign changes of f of x by a positive even number. Well, if you go less than 3 by a positive even number, that would be 2. So 2 less than 3 is 1. So there's either 3 positive real zeros or there's 1 positive real zero. So that tells us about the real zeros on that one. Okay. So now let's talk about this function. Notice here there's a sign change from here to here, and there's a sign change from here to here. And so there's actually 2 sign changes. So there's either 2 positive real zeros or there's no positive real zeros, because 2 minus 2 would be 0. So 2 or none. And here the sign change, there's only 1 sign change. So based on this, it says if f of x has only one variation sign, then f has only one positive real zero. Now, I did this for positive real zeros, but to actually excuse me, determine the number of negative real zeros, you actually have to calculate f of negative x. So f of negative x would be this one. Okay? So for this function, let's see, how many sign changes are there? There is 1, 2, 3. So there are no sign changes in f of x, right? So there's no positive real zeros. And there are 3 sign changes in f of negative x. So that means there are either 3 real negative zeros or 1 real negative zero. Okay? Now, I know you can use technology in order to determine stuff like this, but you know, if you're taking a course involving all of these polynomial theorems, your instructor's going to want you to be able to figure these things out using math and not technology. So always make sure you can do the mathematics behind the technology and don't just rely on the technology. Okay, so that pretty much covers all of those theorems in this section. So now we're going to go on to the next section. Oh, I didn't feel like I did you right there, so let me go back to that theorem. Let's go back to one that we solved earlier. Okay, we found earlier the roots of this, but look at the sign changes in f of x. There's a sign change here, and there's a sign change here, so there's 2 sign changes. So that means this solution has either 2 positive real solutions or 0 positive real solutions. And if you'll remember, when we got to the final answer, we actually had 2, because even though 2 was a single answer, it occurred twice. So you got 2 positive real solutions counting if you count the multiplicity. Now, if I were to calculate this function at negative x, well, let me show you what would happen. If I calculated this at f of negative x to find the negative real solutions, well, all the terms would actually end up being positive. Let's see. I'd have a negative x here, that would be a positive x, and that would be a positive. Okay, so if you replace x with negative x everywhere, you're going to get x to the 4th minus 6x squared plus 8x plus 24. Well, notice there's a sign change from here to here and from here to here. So that's 2 sign changes for f of negative x. So that would tell us about the negative real solutions. But, so there's either got to be 2 negative real solutions or 0 negative real solutions. Well, it turns out that we got 0 negative real solutions, because the only solution we got was, remember, we got the positive real solution 2 twice, and then the other 2 solutions were non-real. So we got no negative real solutions. So it did work. It did work. So you know, that is helpful in determining the number of positive and negative real solutions you might have in a polynomial equation.